This is GMAT 41. You're welcome to our physical chemistry class. In this video, we now look at the topic colligative properties of solution. And of course, not just solution, but dilute solution to be specific. We start first by answering the question, what are colligative properties of a solution? Colligative properties of a solution, just like you see on the board, are properties which depend only on the number of solid particles present in a given solvent. Please take note of the key word there, that they depend on what? The number of solid particles. And these solid particles should be non-volatile. That is, they are those that do not escape, that do not vaporize off from the solution. There are four basic colligative properties. We have them on the board here. Vapor pressure lowering of the solvent. Take note of that, of the solvent. Number two, boiling point elevation of the solution. Not solvent again. Number three, freezing point depression of the solution. And number four, osmosis and osmotic pressure of the solution. As an emphasis, please note that it has been stated here that colligative properties of a solution only depend on what? The number of non-volatile solid particles present. They do not depend on the chemical nature of these particles. Take note. Does not depend on the chemical nature of these particles. They only depend on the number of these particles present. As stated earlier, this solution here is a dilute solution, very dilute one, and ideal. And so it is expected that there is negligible interaction between the solute particles. You see, there are various ways of determining the molecular weight of a substance. One of them is the study of colligative property. That's why when we analyze each of these colligative properties, we're going to use them to determine the molecular weight of the non-volatile solids present in the solution. We now want to talk about the vapor pressure lowering of solvent as a result of the addition of a solid, from which you're going to derive the relative vapor pressure lowering of a solvent. On the board here we have this short note. When you add some non-volatile solute to a solvent, what do you expect to happen? The vapor pressure of this pure solvent will be lowered. Now I'm going to tell you something so you can quickly recall or try to get this concept, because this is something you do in your various homes. Have you ever boiled water before? Okay, maybe you fetch water, pour in your container, maybe a pot, cover it, and then place it on fire. You start heating. As you're heating, what happens? You notice that the water molecule vaporizes due to the addition of heat, and the vapor will start moving upward, isn't it? Now if you remove the cover, the lid of the pot, you will see the vapor like smoke coming out. Is that not so? Now, by the time you add a solute to it, let's assume you decide to pour rice into it, or you decide to add any other solute substance like a solid into it, particle. What happens to this smoke-like vapor that comes out from the water? You will notice that everything will do, going down, right? It's as if maybe you're knocking down the vapor that is coming out as a result of addition of that non-volatile solid. It could be a rice, like I said. Does that make sense? What you've done is actually called lowering of the vapor pressure of that liquid. The water in that case is taken as a pure solvent, so that vapor coming out is the vapor pressure, that is total vapor pressure of the pure water. By the time you add your solutes, that vapor pressure will be lowered. So on the board here, we are saying let that total vapor pressure of the pure solvent be P naught. Is that okay? That is P naught. We are using that to represent it. Then let the partial vapor pressure of the solvent above the solution be P. What do we mean by partial vapor pressure of the solvent above the solution? You know, after knocking down the vapor as a result of adding the solutes, does it mean that all the vapor will get back to the full liquid itself? No. Some of them might still be seen trying to find their way, move out of the container, is that not so? You see them, okay, moving randomly on top of the liquid that you've poured your solid, maybe like rice. You see some vapor just moving, trying to find their way out of the pot. Those are referred to as partial vapor pressure of the solvent above the solution. Now I'm going to ask you, the total vapor pressure of the pure solvent, when you've not added anything, the vapor is just coming out, and the partial vapor pressure of the solvent above the solution when you have added your solid, which one will be greater? Is it going to be the total vapor pressure of the pure solvent or the vapor pressure when you have added a solid? Yes, let me hear from you. Good. That's correct. This will be greater, P naught. That is the total vapor pressure. Because when you have not added any solid, you will see the vapor, finding their way out massively with high kinetic energy, alright? But by the time you have added something, you knock them down. It's just like spiking down the power, alright? The force of the vapor. So you lower it, which means that P naught will be greater than what? P. Now let us take X1 as the mole fraction of the solvent and then X2 as the mole fraction of the solid. These are concepts you're already used to, is that not so? According to a law called Dilute law, is a form of Dalton's law of partial pressure, only that this one operates in dilute end, okay, of the solution. Dilute law, okay? It operates in dilute end of the solution, but Dalton's law operates in concentrated end. That's just the difference between the two. Okay, they are similar. Now, according to Dilute's law, the partial vapor pressure of the solvent above the solution will be equal to mole fraction of the solvent times the total vapor pressure of the solvent. Look at it. If you look at this equation, it's similar to what you saw earlier, okay, before now, under Dalton's law of partial pressure. Good. Now, having said that, we're going to use this Dilute law for this analysis. So what do? Already we have established that P naught will be greater than P. Therefore, there is a change in pressure, P naught minus P, that is the total vapor pressure of the solvent minus the vapor pressure, that is partial vapor pressure of the solvent above the solution. And that we call change in P, that is the difference in P. And this equation 1 is actually the vapor pressure lowering of the solvent. This equation 1, vapor pressure lowering of the solvent. Now we are going to work on this equation 1 to see what we are going to get in terms of the solid, because our aim is to derive this equation in terms of the mole fraction of the solid, so that we can be able to determine the molecular weight of that solid. So we go on. Change in P will now be equal to P naught minus X1 times P naught. You know that this P, partial pressure of the solvent above the solution, according to Dilute's law, is equal to X1 mole fraction of the solvent times what? P naught. So you substitute it for this P. You're going to get this equation. Factorize P naught out, you get this. That is P naught 1 minus X1 will be left. And you recall something, okay? Sum of all mole fraction is equal to 1. Is that not so? Which means as I'm dealing with X1 and X2, X1 plus X2 will be equal to 1. Therefore, if you make X2 subject of formula, it should be 1 minus X1. Is that not so? Mole fraction of the solute will be equal to 1 minus mole fraction of the solvent. Which therefore means that after factorizing your P naught here, this 1 minus X naught is equal to what? X2. That is 1 minus X1 rather is equal to what? X2. Where X2 is mole fraction of what? Of the solute. So all we need to do is to replace this 1 minus X1 with what? X2. And you get this equation 2. This equation 2 is still the same. It's still equal to equation 1. They are both vapor pressure lowering of the pure solvent. Now, if we divide through by P naught, we are going to get this. Divide here by P naught, that is total vapor pressure of the pure solvent. Divide here by P naught, if we cancel, X2 will be left. Now, this equation you saw here, which is the same as this, because change in P is P naught minus P, divided by P naught, is referred to as relative vapor pressure lowering. Relative vapor pressure lowering. Okay, relative vapor pressure lowering of the solvent. So that's what equation 2 is. Now in the next video, we're going to work on this equation 3 rather. We're going to work on it to get this mole fraction and in terms of the molecular weight of the solid. Meanwhile, equation 1, 2, 3, memorize them. I've explained how we obtain them. So in the next video, we are going to see how we introduce molecular weight of the solute to equation 3. Previously, under the vapor pressure lowering of solvent, we established the relative vapor pressure lowering of solvent, where of course we divided the vapor pressure lowering of solvent P minus P naught by P naught. Recall that this quantity is equivalent to mole fraction of the solute, and we call it relative vapor pressure lowering of the what? Solvent, equation 3. Now, what do we know about mole fraction of a component of a solution? In our previous classes, we've established that mole fraction of any component is equal to the number of moles of that component divided by the sum, the total of the number of moles of all the components making up the solution. Here, under this dilute solution, we are discussing a solvent, which is any liquid, as the case might be, then a non-volatile solid. These two components make up the what? The solution. Which means we actually will be talking about, if we are now talking about mole fraction of the solute, X2, is going to be number of moles of the solute, N2, divided by the sum of the number of moles of the solvent and the what? Solute. This is the general formula for mole fraction of a binary solution, a solution containing two components. Now, remember that colligative properties specifically deals with what? Dilute solution. In our trailer video, far backward, we established that a dilute solution is one in which the number of moles of the solvent, N1, is far greater than the number of moles of the solute. This greater means far, okay? If that is the case, it means that we can neglect the number of moles of the solute, which is N2, and then work with the number of moles of the solvent. Once again, I'm going to make you understand this concept. Just imagine you want to make a tea, I say drink tea, and then you get, let's say, your Milo and your milk. Let's say a spoonful of each of them, a spoonful of Milo and milk. Mix them together, that's a solute, okay? And then you add a drum of water into it. That drum of water is your solvent now. Tell me, if you're drinking that tea, will it actually have any taste in your mouth? You won't taste anything. Because the number of moles of the solvent, which is water, is far greater than the number of moles of the solute, which is your milk and Milo that you mixed. Just imagine one spoonful of each solute to a drum of water. So you can neglect the quantity, the number of moles of the solute. That's what we are talking about here, that N1 is far greater than N2, which means we can neglect N2 so that this denominator N1 plus N2 will approximately be equal to what? N1, number of moles of the solvent. So this is the condition for what? Dilute solution. Therefore, mole fraction for dilute solution here is going to be N2 over what? N1. Remember that this N is number of moles, which we know it is the weight or mass of that substance divided by what? Molecular weight or molecular mass of that substance. Therefore, this X2, which is equal to N2 over N1, we can write it in terms of weight and molecular weight and then substitute for X2. That's what I did here. That X2 is equal to number of moles of the solute, which is obtained now from weight of solute over molecular weight of solute, divided by number of moles of solvent, which is obtained from weight of solvent W1 over molecular weight of solvent. If you work around this formula by simplifying, this is what you're going to get. You'll get W2 times N1. This N1 will go up all over. W1 times N2 will come down. So what are we now going to do? We will substitute for this mole fraction using this. And that is why I transferred mole fraction is equal to all this obtained, and it is equal to this relative vapor pressure lowering. Therefore, solve all this and then make N2 subject to the formula. If you make N2 subject to the formula from here, it will be W2 N1 times P naught divided by W1 times P minus P naught. Look at it. And this is the equation actually we are working towards, because recall that our aim here is to determine the molecular weight of the solid. So equation 5 star, very important. Memorize it like never before. And of course, equation alpha star will also guide, because it's a general correlation between all these things we've been working with. This is the definition of each term used here. In the next video, we're going to look at calculations and of course move on to the next colligative property, boiling point elevation of the solution.